The night sky is a beautiful lie. What you see is only a sliver of the light that fills the cosmos, an invisible ocean of the most powerful radiation in existence constantly washes over our planet, a silent fog born from the universe's most violent tantrums. This is the cosmic gamma ray background. It is a pervasive mystery, a faint glow that has no single, obvious source. By the end of this journey, you will understand the 25 greatest puzzles this background poses and how solving them could rewrite fundamental physics. Is this glow the combined scream of every black hole and exploding star since time began? Or is it the telltale signature of an invisible universe of dark matter decaying around us? The story of this invisible light is the ultimate cosmic detective story, and every clue points to a reality stranger than we can see. What hidden truth about the universe do you think is written in this light we cannot see? This fog of gamma rays is the first and greatest mystery. Its origin is the central question that defines all the others. The leading explanation is one of pure cosmic statistics. Picture our universe not as a dark void but as a sea of energetic objects. Each one of these objects, from the supermassive black holes powering distant active galaxies to the furious stellar nurseries in colliding galaxies, can produce gamma rays. Individually, many are too faint and far away for our telescopes to pinpoint, but together, their combined, unresolved light could create the very background glow we see. It is the ultimate example of source confusion, like trying to distinguish the sound of individual raindrops in a thunderstorm. The collective roar becomes a single, pervasive hiss. This theory is elegant and grounded in known physics, relying on the confirmed existence of these violent celestial engines. Yet, even the most careful calculations leave gaps. When astronomers add up the estimated gamma ray output from every known type of galaxy and black hole they can model, the numbers do not always perfectly match the observed intensity and pattern of the background glow. This discrepancy is the crack in the door, the space where stranger possibilities rush in. What if the missing signal is not from ordinary matter at all? An alternative, thrilling idea suggests a portion of this glow could be the death rattle of dark matter. In some theoretical models, when two particles of this invisible substance collide, they could annihilate each other in a flash of energy, producing gamma rays as their final signature. This would mean the faint, uniform fog is not just background noise, but a direct map of the universe's hidden skeleton, the faint glow of dark matter decaying across cosmic time. So the first mystery presents us with a fundamental choice. Is the gamma ray background simply the accumulated echo of a million cosmic catastrophes we already understand? Or is it our first glimpse into a shadow universe written in light we are only beginning to read? The answer shapes everything that follows. This discrepancy leads us directly into the second great mystery, one that challenges our understanding of the cosmos's most powerful engines. We call it the missing blazar problem. Blazars are among the most violent objects in the universe. Imagine a supermassive black hole at the heart of a distant galaxy, not just consuming matter but launching a pair of magnetized particle beams or jets out into space at nearly the speed of light. By pure cosmic chance, one of those deadly lances is pointed directly at Earth. From our perspective, that jet is amplified, appearing incredibly bright across the entire electromagnetic spectrum, especially in gamma rays. These blazars are the lighthouse beacons of the high-energy sky, and for a long time, astronomers thought they were the prime suspects for creating the gamma ray background. The logic was sound. Take all the blazars we can see, estimate how many more must exist at fainter levels and greater distances, add up their theoretical gamma ray output, and the total should account for a significant portion, if not all, of that mysterious fog. But the data from instruments like the Fermi Large Area Telescope told a different story. When scientists performed this cosmic accounting, they found a glaring gap. The combined glow from all the blazars we know of and predict to exist simply does not add up to the observed intensity of the cosmic gamma ray background. There is a significant portion of that fog that blazars cannot explain. This forces a profound and unsettling question. Are our models for how many blazars exist in the universe completely wrong? Perhaps there is an entire population of hidden blazars we are missing, ones whose jets are pointed just slightly away from us, making them far dimmer in our telescopes. Or, more intriguingly, does this gap mean that an entirely different class of cosmic object is responsible for the majority of the background glow? The search for these hidden blazars is ongoing, a meticulous effort to find faint, misaligned versions of these monsters. Yet if they remain elusive, the implication is staggering. It means the dominant source of the most powerful radiation bathing our universe is not the thing we thought was the brightest. It is something else, something perhaps more numerous, more subtle, or far more exotic, waiting in the shadows of our data. The hunt for the missing gamma rays leads us away from the most violent monsters and toward the seemingly ordinary. If blazars cannot account for the entire fog, perhaps the answer lies in the combined glow of billions of galaxies like our own. This is the third mystery, the quiet but immense contribution of star-forming galaxies. Our Milky Way is not a peaceful place. Between its shimmering spiral arms, a relentless storm of cosmic rays, which are atomic nuclei accelerated to nearly light speed, constantly rages. These particles do not travel peacefully. They slam into the vast clouds of hydrogen gas that drift between the stars. Each collision is a miniature cataclysm, creating unstable particles called pions that almost instantly decay into gamma rays. This process, known as pion decay, turns every star-forming galaxy into a faint, glowing halo of high-energy light. The Milky Way itself is a source of gamma rays, and we sit right inside its diffuse glow. Now scale this up to the entire observable universe. Every galaxy where stars are being born is doing the same thing, filling its own space with this secondary gamma ray light. When you add up the potential output from all these countless galaxies across cosmic time, the numbers become compelling. Some estimates suggest that this collective hum from ordinary galaxies could account for a staggering half of the entire cosmic gamma ray background. It is a beautifully simple idea, the universe's background noise created by the combined sigh of a trillion interstellar storms, yet here lies the profound uncertainty. To make this calculation, we must know the density of cosmic rays inside galaxies billions of light years away, galaxies we see only as faint smudges of visible light. We cannot measure their internal particle storms directly. We have to extrapolate from what we see in our own galaxy and a few nearby neighbors, assuming the rules are the same everywhere. But what if they are not? What if galaxies in the early universe, smaller and more chaotic, were far richer in cosmic rays, or perhaps they were poorer? This uncertainty means the role of these normal galaxies is both a promising solution and a major variable. They could be the dominant source we have overlooked, or they could only be a supporting player. The answer is written in the faint gamma ray halos of distant spirals, a signal we are only now learning to read. It forces us to ask, is the universe's most powerful light mostly the product of its most common, everyday processes, or does it still demand something truly extraordinary? The quiet hum of distant galaxies may explain much of the fog, but it cannot account for its most unsettling feature. When astronomers dissect the cosmic gamma ray background not just by its brightness but by its color, a deeper anomaly emerges. This is the fourth mystery, the high-energy excess. Think of the background glow as a cosmic rainbow but for gamma rays. At one end are lower-energy gamma rays, and at the far end are the most powerful, highest-energy photons. According to our best models, the combined light from known sources like blazars and star-forming galaxies should create a predictable slope in this rainbow. The highest energy part should fade away more quickly, but the data reveals something different. Above about 50 gigaelectronvolts, a unit of energy that marks the extreme frontier, the background does not fade as expected. It remains stubbornly bright. There is an excess of this ultra-powerful radiation, a bump in the spectrum that our standard catalog of cosmic objects cannot easily produce. This is not a small discrepancy. It is a glaring clue that something is fundamentally missing from our equation. One of the most compelling explanations for this excess reaches into the realm of the invisible. Certain theoretical candidates for dark matter, particles known as weakly interacting massive particles or WIMP, could be the source. If these particles exist, they might occasionally collide and annihilate one another. The energy released from such an event would be titanic, often producing gamma rays right in this exact high energy range. If this is true, then the high energy excess is not an astrophysical curiosity, it is a direct signal. It is the faint, collective glow of dark matter dying across the universe, a shadow universe revealing itself through its final flash of light. The prospect is breathtaking, but scientists must rule out every ordinary possibility first. Could the excess come from a special breed of blazars we have not yet identified, ones with jets that somehow produce an unusually high proportion of these hard, penetrating gamma rays? Or perhaps it is a secondary effect, a cascade of light created when ultra-high-energy cosmic rays, the most energetic particles known, smash into the faint background light that fills the cosmos, creating a shower of gamma rays. Each of these astrophysical explanations is plausible, yet each requires its own set of unusual conditions. The hunt, therefore, becomes a process of elimination. Is the bump in the day to the signature of a new class of cosmic accelerator, or is it the long-sought evidence of a hidden component of reality itself? The answer lies in that persistent, unexplained glow at the very edge of our perception. This smoothness is the fifth great mystery, the isotropy enigma. If you could see the universe in gamma rays, you would not see a sky filled with distinct points of light. You would see a nearly uniform, featureless fog. It is not perfectly smooth, there are subtle variations, but it is remarkably isotropic. It looks roughly the same in every direction you point your telescope. This is deeply puzzling. Consider the known structure of the cosmos. Galaxies are not scattered randomly like salt on a table. They are arranged in a vast cosmic web, an intricate architecture of dense clusters, long filaments, and enormous empty voids. This is the large-scale structure of the universe, a lumpy, clumpy distribution of matter. If the gamma-ray background is simply the combined light of all those galaxies, whether from their black holes or their star-forming storms, then the background map should reflect that lumpiness. We should see brighter patches corresponding to the dense clusters and filaments, and darker patches over the voids. It should look like a glowing outline of the cosmic web. But it does not. The gamma-ray sky is far smoother than the distribution of galaxies. This presents a cosmic riddle. How can a collection of discrete, clumped sources produce a glow that is so uniform? One possibility is that the sources are just incredibly numerous. If there are enough faint gamma-ray emitters, trillions upon trillions of them spread throughout space, their individual points of light could blend together into a seamless glow, much like the individual pixels on a screen merge into a single, smooth image from a distance. The sheer number of sources would wash out the lumpiness of the cosmic web. The other, more radical possibility is that we are not looking at the light of countless individual objects at all. The smoothness could be a sign of a truly diffuse process, something that fills the universe evenly like a gas. This is where the dark matter hypothesis gains more traction. If the gamma rays are produced by dark matter particles decaying or annihilating throughout the cosmos, and if dark matter is itself smoothly distributed on large scales, then the resulting glow would be isotropic. It would be a perfect, uniform signature of an invisible universe permeating our own. So the isotropy enigma forces a choice between two profoundly different views of reality. Is the gamma-ray fog the ultimate statistical average, the blended light of every single violent event in history, so numerous that the universe's structure disappears? Or is it the first direct image of the dark matter halo that cradles the entire cosmos, a shadow made visible by its own faint, dying light? The smoothness of the sky may be the most important clue we have. The smooth fog of gamma rays may hold the answer to another, even more extreme cosmic mystery. The universe is not just filled with light, it is under constant bombardment by atomic nuclei traveling at a fraction below the speed of light. These are ultra-high-energy cosmic rays, the most energetic particles ever detected, and their origin is one of the greatest puzzles in astrophysics. Where do they come from? The leading suspects are the most violent engines imaginable, like the jets from active galaxies or the aftermath of colliding galaxies. But there is a fundamental problem with these particles traveling across the vast distances of the universe. As they fly through space, they do not travel through a perfect vacuum. They must plow through the faint relic glow of the Big Bang itself, the cosmic microwave background radiation. This bath of ancient photons acts like a cosmic fog for these ultra-fast particles. When a proton traveling at nearly light speed collides with one of these microwave photons, the interaction is catastrophic. It triggers a process known as the Greisen-Zatsepin-Kuzmin effect, or the GZK cutoff. In simple terms, the ultra-high-energy cosmic ray loses a tremendous amount of energy in the collision, creating a shower of secondary particles. And crucially, that shower includes gamma rays and ghostly particles called neutrinos. This means that if ultra-high-energy cosmic rays are produced in distant galaxies and travel to us, their journey should be marked by a trail of gamma-ray light, a faint cascade created by their constant collisions with the cosmic microwave background. This leads to a thrilling possibility. A portion of the smooth, isotropic cosmic gamma-ray background could be this very cascade, the accumulated fallout from the universe's most powerful particle accelerators. Finding this specific component within the gamma-ray fog would be a monumental discovery. It would be the smoking gun, directly linking the background to the origin of these mysterious particles. It would tell us not just that these cosmic rays exist, but map out their journey through the cosmos. The challenge, however, is immense. Separating this hypothetical GZK cascade from all the other gamma-ray sources is like trying to hear a single instrument in a symphony played by a million orchestras. The signal from the cascade would be extremely faint and diffuse, blending perfectly into the very isotropic smoothness that makes the background so mysterious. Scientists must use sophisticated models to predict the precise energy signature of these cascade gamma rays, and then scour the data from telescopes like Fermi for that specific pattern. It is a needle in a haystack search on a cosmic scale. If they succeed, it will solve two profound mysteries at once, revealing the gamma-ray background as the final echo of the universe's most powerful particle collisions. But this fog of gamma rays is more than just a signal, it is also a filter. The universe is not perfectly transparent to its own most powerful light. This leads us to the seventh mystery, the story written in the missing light, a phenomenon known as extragalactic background light absorption. Gamma rays, for all their penetrating power, do not travel across billions of light years completely unimpeded. Their journey is a perilous one filled with invisible obstacles. The space between galaxies is not empty. It is filled with a faint, ancient glow called the extragalactic background light. This is not one single light, but the combined total of all the starlight ever produced in the history of the universe, plus the infrared glow from cosmic dust warmed by that starlight. It is the accumulated warmth of every sun that has ever shone, still echoing through the cosmos. When a high-energy gamma-ray photon, speeding across the void, meets one of these lower-energy background light photons, something extraordinary happens. They can annihilate each other. The collision converts their energy into matter, typically producing an electron and its antimatter counterpart, a positron. From our perspective, the gamma ray simply vanishes. It has been absorbed. This means the universe becomes increasingly opaque to the highest energy gamma rays the farther they try to travel. A gamma ray born in a distant blazar 10 billion light-years away has a much lower chance of reaching us than one from a source only a billion light-years away, because its long journey gives it more opportunities for a fatal collision. We see this effect in the cosmic gamma ray background spectrum itself. At the very highest energies, there is a noticeable drop-off, a softening of the glow. This is not because those gamma rays were never emitted, but because a significant fraction of them have been filtered out by the extragalactic background light during their epic voyages. Here is where the mystery transforms into a powerful tool. By carefully measuring this absorption, by analyzing exactly how the gamma ray background dims at specific high energies, astronomers can do something incredible. They can reverse engineer the properties of the extragalactic background light itself. It is like studying the shadow cast by an unseen object to deduce the object's shape. The absorption features in the gamma ray fog tell us the density and the spectrum of that total starlight across cosmic time. This allows us to measure, in a completely independent way, the total history of star formation in the universe. It is a cosmic census conducted not by counting individual stars, but by reading the faint stain they left on the most powerful radiation flying past them. So this mystery is a beautiful duality. The extragalactic background light acts as a veil, obscuring our view of the most distant gamma ray sources, but in doing so, it imprints its own signature on the light that does get through. The gamma ray background becomes a backlight, illuminating the very substance that seeks to block it, giving us a unique and profound measure of all the light ever created. The absorption of gamma rays by ancient starlight is a story of cosmic journeys ending, but some of the most violent events in the universe leave a much longer echo. Gamma ray bursts are the cosmos's ultimate flashbang. In a few fleeting seconds, a single burst can outshine every star in a galaxy, releasing more energy than our sun will in its entire 10 billion-year lifetime. For decades, we believed the story ended there, a brilliant flash and then darkness, but we were wrong. The real mystery begins after the blinding light fades. What follows is a long-lived afterglow, a remnant of the explosion that can shine across the electromagnetic spectrum for days, weeks, or even years, and yes, that includes gamma rays. This leads us to the eighth great mystery of the cosmic gamma ray background. Could the combined, lingering glow from every gamma ray burst that has ever occurred, scattered across all of cosmic time, be a significant piece of the puzzle? Imagine a dark forest after a lightning strike. The flash is instantaneous, but the embers of the struck tree smolder for hours, casting a faint, persistent light. Now imagine that forest is the universe, and the lightning strikes are these titanic explosions happening at random, one every few days somewhere in the observable cosmos. While the initial flash is pointed and directional, the afterglow is more of a fading cloud, expanding and radiating in many directions. The calculation is staggering in its scale and its uncertainty. To estimate the contribution, scientists must answer two incredibly difficult questions. First, how many gamma ray bursts have actually occurred throughout the history of the universe? We only see the ones whose narrow, initial jets are pointed almost directly at Earth, which is a tiny fraction of the total. The true rate, especially in the early universe, is a huge unknown. Second, how bright and how long do their gamma ray afterglows truly last? Our observations are limited to a handful of nearby bursts we have been lucky enough to catch. We must extrapolate their behavior across billions of years, not knowing if the properties of these explosions or their environments changed over cosmic time. The models that attempt this cosmic sum produce a fascinating range of answers. Some suggest the integrated light from all these fading embers could contribute a few percent to the overall gamma-ray fog, a small but meaningful piece. Others propose that under certain conditions, with particularly bright and long-lived afterglows, the contribution could be far more substantial. This uncertainty makes gamma-ray burst afterglows a tantalizing wild card. They represent a known phenomenon with potentially massive, unresolved consequences. They are not an exotic new particle, but a familiar cataclysm whose full historical impact we are only beginning to grasp. Each fading afterglow we study today is a clue to the invisible light of a million similar explosions lost to time, their final whispers perhaps still bathing us in a faint, omnipresent glow. The fading embers of gamma-ray bursts are not the only hidden contributors to the cosmic fog. There exists another, quieter class of giants whose influence may be vastly underestimated. These are the radio galaxies, and they present the ninth great mystery of the gamma-ray background. If blazars are the blinding lighthouses pointed directly at us, radio galaxies are their more common cousins seen from the side. Their central supermassive black holes still launch those devastating relativistic jets, but the beams are angled away from our line of sight. We do not see the searing, direct beam. Instead, we see the aftermath. Where those jets plow into the intergalactic medium at their ends, they create colossal, ballooning structures called lobes. These lobes are immense reservoirs of magnetized plasma and particles accelerated to nearly the speed of light, and they can span millions of light years. They are cosmic accelerators on a truly monstrous scale. For a long time, we thought of these lobes as radio wave factories, which is how we discovered and named them. But we now know they are also powerful sources of gamma rays. The frantic electrons spiraling in the lobe's magnetic fields and the collisions within that turbulent plasma can generate high-energy photons. Our own galactic neighbor, Centaurus A, displays these giant, ghostly lobes clearly, and it is a confirmed source of gamma rays. Here lies the pivotal question. Radio galaxies are far more common in the universe than their flashy blazar relatives. If every massive galaxy goes through a radio-loud phase in its life, and each one of those phases builds these gamma-ray-producing lobes, then their combined cumulative output could be enormous. They could represent the quiet majority of gamma-ray sources, a pervasive hum underlying the more dramatic flashes from blazars and bursts. The challenge is one of cosmic distance and sensitivity. While we can easily see the radio lobes of a nearby galaxy like Centaurus A, detecting the faint gamma-ray signal from a single radio galaxy billions of light-years away is extremely difficult. Their gamma-ray emission is diffuse, spread across those gigantic lobes, making it hard to pinpoint against the background fog. This creates a profound uncertainty. We know these objects produce gamma rays. We just do not know how many there are across the depth of the universe or exactly how efficient they are at it. Their total contribution to the background glow is therefore a major unknown. They could be a dominant, steady source we have been overlooking simply because we see them from an unflattering angle. The secret life of radio galaxies forces us to reconsider the census of the high-energy sky. Is the gamma-ray fog not the scream of the rare monsters pointed at us, but the accumulated sigh of a trillion quieter giants, their hidden engines slowly filling the cosmos with power? Beyond the quiet giants, the cosmos is also littered with the spinning corpses of dead stars. These neutron stars, born in supernova explosions, can rotate at dizzying speeds, whipping their immense magnetic fields around like cosmic lighthouses. And around some of the most energetic of these pulsars, something spectacular forms, a pulsar wind nebula. This is the 10th mystery hidden within the gamma-ray fog. Picture the Crab Nebula, that beautiful, tangled remnant of a star that exploded nearly 1,000 years ago. At its heart spins a pulsar, a city-sized ball of matter so dense a teaspoon of it would weigh 1 billion tons. This pulsar does not just spin, it blows. It generates a hurricane of charged particles, a relentless wind that streams outward at nearly the speed of light. This wind slams into the slower-moving debris of the ancient supernova, creating a shock wave that lights up the entire nebula. That glow is not just visible light, it is a blaze of radiation from radio waves all the way up to gamma rays. The Crab Nebula is a brilliant, nearby example of a pulsar wind nebula, a temporary bubble of furious energy that can shine for tens of thousands of years before fading. The question for the cosmic gamma-ray background is one of sheer numbers. Our Milky Way is home to a catalogue of these brilliant objects, but what about every other galaxy? Every spiral, every elliptical, every dwarf galaxy that has ever hosted a supernova has likely produced its own population of pulsar wind nebulae, each one a bright, compact source of gamma rays for a cosmic instant. Could the combined output of all these ephemeral bubbles scattered across space and time add up to a measurable portion of the universal background glow? The challenge is profound. We understand the physics of the Crab Nebula in exquisite detail because it is in our backyard. But to extrapolate from that single, famous example to the trillions of nebulae in the distant universe requires a leap of faith. We must guess how often pulsars are born with the right spin and magnetic field to create such powerful winds. We must estimate how long their nebulae shine brightly in gamma rays before their expanding bubbles grow too thin and dim. And we must account for galaxies in the early universe, which may have had very different rates of star death and birth. It is a cosmic census of ghosts, counting the faded glow of stellar remnants we can no longer see. Some models suggest that while individual pulsar wind nebulae are bright, they are too short-lived and too rare to dominate the background. Others propose that if the conditions are just right, their collective sparkle could be a significant, shimmering thread woven into the fabric of the gamma-ray fog. The answer lies in the faint, unresolved light of galaxies far, far away, where the combined whisper of a billion crab-like nebulas might still echo. The most profound explanation for the gamma-ray fog reaches into a universe we cannot see. This is the 11th mystery, the hunt for a dark matter annihilation signal. For decades, dark matter has been a ghost in the cosmic machine, its presence felt only by its immense gravitational pull on galaxies and clusters. We know it makes up about 85% of the matter in the cosmos, yet we have no idea what it is made of. One of the leading theoretical candidates is a class of particles known as weakly interacting massive particles, or WIMP. The name tells the story. They are massive, meaning they carry significant heft. They are weakly interacting, meaning they barely touch normal matter, passing through our planet and our bodies as if they were not there. But here is the critical idea. While they ignore ordinary atoms, they might not ignore each other. According to some models, when two WIMP particles collide, they can annihilate one another in a flash of pure energy. That energy, in turn, could transform into a cascade of secondary particles, and among them would be gamma rays. If this process is happening throughout the vast halos of dark matter that surround every galaxy and permeate the spaces between them, then the entire cosmos should be faintly glowing with the gamma ray signature of dark matter dying. The cosmic gamma-ray background would be that glow, the final, universal flash of an invisible substance revealing itself. Astronomers are not searching for just any random bump in the data, however. They are looking for a very specific fingerprint. If dark matter particles all have the same mass, their annihilation would produce gamma rays with a very specific characteristic energy. Imagine tuning a radio and hearing a single, pure tone rise above the static. In the gamma-ray spectrum, this would appear as a sharp, narrow line at a precise energy, a smoking gun signature that ordinary astrophysical processes like supernova or black hole jets simply cannot produce. No such definitive line has been found yet. The other signature is a broader bump or excess in the spectrum, like the high-energy excess we discussed earlier. but with a shape that matches predictions from specific dark matter models. Finding either of these signals hidden within the smooth, isotropic fog would be a discovery of Nobel Prize magnitude. It would solve two of the greatest mysteries in modern science at once. We would finally know the identity of the universe's dominant form of matter, and we would have identified a major, perhaps even dominant, source of the cosmic gamma-ray background. The fog would transform from an astrophysical puzzle into a direct window into a shadow universe, a map of the dark written in the only language it might ever speak, light. The dark matter hypothesis is grounded in elegant particle physics, but there is another, even more exotic possibility hiding in the cosmic background. Stephen Hawking gave us one of the most startling predictions in all of theoretical physics. Black holes, he proposed, are not perfectly black. Due to bizarre quantum effects at their very boundary, they should slowly leak energy, radiating it away into space. For a stellar mass or supermassive black hole, this Hawking radiation is utterly insignificant, a trickle compared to their immense size. But for a hypothetical creature of the early universe, this process is everything. Imagine a black hole not forged in the death of a star, but born in the incredible density fluctuations of the Big Bang itself. These would be primordial black holes, and they could have been created with almost any mass from mountain size to planet size. A black hole the mass of a small asteroid, according to Hawking's math, would have been radiating away for most of the age of the universe, and its end would not be quiet. As it evaporates, it loses mass, which makes it radiate faster in a runaway process that culminates in a final, explosive flash. In its last second of existence, such a tiny black hole would release a burst of energy equivalent to 1,000,001 megaton nuclear bombs, most of it in the form of high-energy gamma rays. Now, let us scale this idea to the cosmos. If the early universe was seeded with vast numbers of these tiny, quantum-scale black holes, their death spasms would be happening all the time, everywhere. Each one a minuscule final fireworks display. Could the combined light of a trillion such evaporations, scattered across space and time, be the source of the smooth, isotropic gamma-ray background we see? It is a breathtakingly speculative idea, connecting the quantum weirdness of black holes to the largest-scale glow in the universe. The challenge, however, is one of observation. If these explosions are happening, why have we not seen one directly? Gamma-ray telescopes have scanned the skies for decades, and while they catch plenty of bursts from stellar cataclysms, none have the unmistakable, predicted signature of a primordial black hole popping out of existence. This non-detection places severe limits on how many of these objects could exist today. They cannot be so numerous that their final bursts would light up our sky like a constant fireworks show. But here is where the diffuse background offers a loophole, a population of primordial black holes that is just below the threshold for direct detection, whose individual bursts are too faint or too infrequent for us to pinpoint, could still collectively add up to a faint, uniform glow. Their combined signal would blend seamlessly into the cosmic fog, a whisper lost in the chorus. So while the direct search for these evaporating black holes has so far come up empty, the gamma-ray background itself remains a potential hiding place for their accumulated legacy. It is a long shot, a fringe idea dancing on the edge of known physics, but it reminds us that the answer to this cosmic mystery might not lie in the stars we see, but in the forgotten relics of creation itself. The faint glow of the cosmic background may hold a map of invisible forces stretching between the galaxies themselves. This is the 13th mystery, the intergalactic magnetic field puzzle. We often think of the space between galaxies as a true void, an empty stage where light travels unimpeded. But it is not entirely empty. It is threaded with the faintest traces of magnetism, a ghostly web of force fields that likely formed in the universe's infancy and have been stretched and woven by cosmic flows ever since. These intergalactic magnetic fields are unimaginably weak, millions of times fainter than Earth's own magnetic field, and detecting them directly has been nearly impossible. Yet they may leave their signature on the gamma-ray fog in a subtle and brilliant way. The process involves a cosmic detour. Remember, gamma rays are often created alongside other particles, especially when high-energy processes are at work. A common chain of events goes like this. A gamma ray, perhaps from a distant blazar, travels through space. It then collides with a photon from the extragalactic background light, annihilating to produce a pair of particles, an electron and its antimatter twin, a positron. These charged particles are then caught in the cosmic web. They do not travel in straight lines. Instead, they are captured by those faint intergalactic magnetic fields, forced to spiral along the magnetic lines in a wild, chaotic dance. As they whirl, they lose energy, emitting new gamma rays in the process. This secondary light then continues toward us. The result is a kind of cosmic blurring. The gamma rays we finally detect in our telescopes are not necessarily coming directly from their original source. They have been reprocessed, their journey scrambled by magnetic fields we cannot see. The original point of light has been smeared into a faint, diffuse halo. This has a direct effect on the cosmic gamma-ray background. If this process is widespread, it means a portion of that smooth, isotropic fog might not be the direct light from sources at all, but this secondary, reprocessed glow. The properties of the background, its exact smoothness, its spectrum, could encode information about the strength and the tangled structure of those invisible magnetic fields. By carefully analyzing the statistical patterns in the gamma-ray fog, astronomers hope to perform a remarkable feat of reverse engineering. They are using the universe's most energetic light as a probe, tracing the invisible magnetic skeleton of the cosmos. It is like trying to deduce the shape of a maze by studying the scattered light that finally escapes its walls. Solving this puzzle would unlock a new understanding of cosmic evolution, revealing how the first magnetic seeds were planted and how they grew to shape the vast spaces between galaxies. The invisible storms raging inside distant galaxies hold a secret about their own nature. Our 14th mystery asks a fundamental question about the cosmic rays that fill them. Are those particle hurricanes made mostly of protons, the heavy nuclei of hydrogen atoms, or are they dominated by lightweight electrons? The answer is not just academic, it is written directly into the gamma-ray fog. When a proton cosmic ray smashes into a hydrogen atom in an interstellar cloud, the collision creates unstable particles called pions. These pions then decay, producing a very specific and predictable spectrum of gamma rays, a kind of energy fingerprint. Electrons, on the other hand, produce gamma rays through a different process, often by scattering off lower energy photons, which leaves a different spectral signature. The cosmic gamma-ray background, as the combined light of all these star-forming galaxies, becomes a cosmic averaging machine. By dissecting its spectrum with exquisite care, astronomers can search for that telltale proton fingerprint. Finding it would be a monumental discovery. It would tell us that across the universe, in galaxies large and small, the primary engines of particle acceleration, likely supernova shockwaves, are overwhelmingly tuned to launch heavy protons to incredible speeds. This proton dominance would reveal a universal preference in the laws of astrophysical acceleration, a rule that holds from our Milky Way to the farthest spirals we can see. But if the background spectrum lacks that clear proton signature, the implication is just as profound. It would suggest that electron acceleration is far more common or efficient than we thought, or that other, more exotic processes are at work within the hearts of galaxies. This single measurement, teased from the smooth glow, gives us a direct probe into the inner workings of 1 trillion galactic engines all at once. It is like listening to the combined roar of every storm on a planet to determine if they are all made of rain or hail. The gamma-ray background, therefore, is more than a puzzle to solve. It is a tool. It allows us to take a census of cosmic violence on a scale we could never achieve by studying galaxies one by one. Our own galaxy is not a passive bystander in this cosmic story. It is a contributor, and it holds a clue in the form of a local mystery that echoes across the universe. Rising from the heart of the Milky Way, stretching for 25,000 light-years above and below the galactic plane, are two colossal, ghostly structures known as the Fermi bubbles. These are not made of stars or gas in the traditional sense. They are immense balloons of ultra-hot plasma, glowing faintly in the very gamma-ray light we have been discussing. They are a monument to a cataclysm in our own backyard, a past eruption from the supermassive black hole at our galactic center, Sagittarius A star. This eruption, likely a titanic outburst of energy and matter, blew these bubbles into the galactic halo millions of years ago, and they are still shining today. This local phenomenon forces a profound question for the cosmic gamma-ray background. If our ordinary spiral galaxy produced such enormous, long-lasting gamma-ray structures, then surely other galaxies have too. Every spiral, every elliptical with a central black hole could have experienced similar eruptions throughout its history. Each event would leave behind its own set of fading Fermi-like bubbles, giant gamma-ray halos that could persist for eons. Now picture the universe filled with billions of galaxies, each potentially surrounded by these faint, gargantuan ghosts. From our distant vantage point, we could never resolve an individual bubble around another galaxy. Their immense, diffuse glow would simply blend into the general haze of the extragalactic sky. The combined, unresolved light from all the galactic Fermi bubbles in the cosmos could be seeping directly into the background fog we are trying to decipher. This links a local, active area of research mystery directly to the grandest cosmic one. Understanding what created our bubbles, whether it was a single violent outburst or a series of smaller events, tells us how common such eruptions might be in the life cycle of a typical galaxy. If they are a regular phase, like a galactic volcano erupting every few 100 million years, then their contribution to the background could be substantial. They represent a known class of object with a measurable output right here in our own home, giving us a template to estimate their universal influence. The Fermi bubbles are a bridge. They remind us that the cosmic fog is not just the light of distant alien cataclysms. It is also the accumulated breath of every galaxy, including our own, exhaling its history into the void. The highest energy gamma rays face a cosmic dead end. This brings us to a fascinating technical crisis known as the TV catastrophe. TV stands for teraelectronvolt, a unit of energy so immense it represents gamma rays 1 trillion times more powerful than visible light photons. Ground-based observatories like Hawk in Mexico and LOSO in China are masters at catching these monstrous particles. They do not use traditional mirrors. Instead, they watch for the faint, blue flashes of Cherenkov light created when a TV gamma ray smashes into Earth's upper atmosphere, creating a shower of secondary particles. These instruments have opened a new window on the most violent events in the nearby universe. But there is a fundamental expectation here, one rooted in the absorption we discussed earlier. The extragalactic background light, that total history of starlight, acts as an impenetrable wall for TV gamma rays traveling across intergalactic space. Over distances of even a few 100 million light-years, the probability of a TV photon surviving a collision with a background light photon and reaching us drops to nearly zero. Therefore, our models predict that the cosmic background glow at these energies should be almost non-existent. The TV sky should be mostly dark, punctuated only by the rare, brilliant flashes of very nearby sources. This is not just a prediction, it is a cornerstone of our understanding of gamma-ray propagation through the universe. Now, imagine the catastrophe. What if these incredibly sensitive next-generation telescopes, after years of careful observation, begin to detect a faint but persistent TV background? A diffuse glow where none should exist. This would be more than a puzzle, it would be a crisis. It would mean something in our chain of reasoning is profoundly broken. One possibility is that our measurement of the extragalactic background light is wrong, that the universe is more transparent at these energies than we thought. Another is that there exists a previously unknown population of extremely powerful TV sources in our own galactic backyard, so close that their light has not had time to be absorbed, yet so numerous and faint they blend into a uniform glow. The most thrilling possibility, however, touches on new physics. Perhaps the gamma rays are not surviving the journey in the conventional way. Some exotic theories suggest that TV photons could oscillate into hypothetical, lightweight particles called actions as they traverse intergalactic magnetic fields. These actions would ignore the starlight barrier completely, traveling unimpeded before converting back into gamma rays closer to Earth, effectively tunneling through the wall. A detected TV background would force us to confront these radical ideas. It is a high-stakes search at the very edge of detection, where finding a signal would be as disruptive as not finding one. The silence confirms our universe, but a whisper at these energies could shatter it. The fate of a star can be a slow fade or a spectacular public execution. In the dense cores of galaxies, stars sometimes wander into the fatal gravity of the supermassive black hole lurking there. This is a tidal disruption event, and it is one of the most violent single acts in the cosmos. As the star approaches, the black hole's tidal forces become overwhelming. The side of the star facing the monster feels a much stronger pull than the side facing away. This difference stretches the star into a long, thin strand of superheated plasma, a process literally called spaghettification. Much of this stellar material is then flung out into space or forms a swirling, screaming accretion disk around the black hole, heating to millions of degrees and producing a brilliant flare of light that can outshine its host galaxy for months. For a long time, we observed these events mainly in optical and ultraviolet light, but recently our gamma-ray telescopes have caught a few of them in the act, shining with high-energy fury. This discovery adds a new, flickering candidate to the list of background contributors. The math is one of cosmic probability. In a given galaxy, a tidal disruption event is exceedingly rare, happening maybe once every 10,000 to 100,000 years. But the universe contains upwards of 200 billion galaxies. At any moment, somewhere in the observable cosmos, a star is being shredded. While each individual flare is transient, the combined light from all these ongoing stellar executions happening across space and time could, in theory, add up to a persistent, if faint, component of the gamma-ray fog. It would be the universe's background flicker of constant, distant cataclysms. Estimating their true contribution, however, is a monumental challenge wrapped in unpredictability. We do not yet know if every tidal disruption event produces a strong gamma-ray signal, or only a special subset under specific conditions. Does the black hole spin matter? The type of star, the angle at which we see it, our sample size of gamma-ray bright events is still tiny, making any extrapolation to the entire cosmos a shot in the dark. Furthermore, the flare's behavior is chaotic. Unlike a pulsar's steady beat, a tidal disruption event's gamma-ray output can spike and fade erratically as the stellar debris falls in uneven clumps onto the black hole. This makes modeling their long-term, averaged light incredibly difficult. They are the cosmic equivalent of unpredictable flashbulbs popping off in a vast dark room. Could their combined, strobing light be a significant part of the background glow we measure? Or are they simply rare, brilliant punctuation marks in a story written by quieter, more constant sources? Each new gamma-ray tidal disruption event we detect is a precious data point, helping us understand whether these stellar deaths are a footnote in the history of the gamma-ray sky, or a recurring chapter that has subtly shaped the light of the cosmos. Supernova remnants are the ghostly aftermath of stellar death, and they are the undisputed engines of our galaxy's cosmic ray storm. For over a century, we have known that the shock waves from these expanding shells of debris are the most powerful particle accelerators in the Milky Way, capable of launching protons and electrons to nearly the speed of light. And where you have these frantic particles, you get gamma rays as they collide with interstellar gas or radiate energy in magnetic fields. The Crab Nebula, the Vela Remnant, and others are bright, nearby beacons in our gamma-ray sky. This local fact presents an immense question for the cosmic background. If every star-forming galaxy is filled with these remnants, and each one is a prolific cosmic ray factory, then their combined gamma-ray output across the universe must be staggering. They should be a dominant source of the extragalactic fog, but the reality is far more nuanced, a true conundrum. The contribution of a single supernova remnant to the gamma-ray sky depends on two critical and variable factors. First, how good is the remnant at its job? The shockwave must not only accelerate particles, it must trap them within its expanding shell long enough for them to gain tremendous energy and produce gamma rays. A remnant with a strong, turbulent magnetic field is a perfect prison, keeping particles bouncing back and forth for thousands of years. A weaker field lets them escape too quickly, reducing the gamma-ray yield. Second, the remnant needs fuel. Those accelerated particles produce the most gamma rays when they slam into the dense molecular clouds that often surround the sites of stellar death. A remnant expanding into a barren region of space will be a far dimmer source. So, to understand their universal role, we must ask, are the conditions in our galaxy typical? Is the Milky Way's mix of magnetic field strength and gas density the standard recipe for a bright gamma-ray remnant? Or are we living in a special, optimized cosmic ray factory? If our local remnants represent the high-efficiency end of the spectrum, then supernova in distant, more diffuse galaxies might contribute far less to the background than a simple extrapolation would suggest. Their faint, dispersed glow could be lost in the noise, but if the physics is universal and every spiral galaxy's interstellar medium is similarly primed for particle acceleration, then the collective sigh of 100 billion supernova remnants could be a fundamental bass note in the gamma-ray chorus. This mystery forces us to use the smooth background as a laboratory. By analyzing its spectrum, we are indirectly testing the uniformity of astrophysical laws across cosmic time and space. Are the rules of shock acceleration and particle confinement the same everywhere? Or does the universe allow for a wild diversity in how it builds its engines? The answer is written in the faint, accumulated light of stellar graves we will never see. The laws of physics we know and love are incomplete. This is not a philosophical statement, but a concrete fact written into our most fundamental theories. The Standard Model of particle physics describes the menagerie of subatomic particles and forces that build our reality, but it is silent on dark matter and fails to explain several deep cosmic puzzles. This gap is where some of the most imaginative science lives, and it brings us to the 19th mystery of the gamma-ray background, a search for ghosts within the machine. We are hunting for action like particles or ALP. These are not the dark matter candidate WIMP we discussed earlier. They are something else entirely, hypothetical particles predicted by some extensions to the Standard Model, particles so lightweight and weakly interacting they could pass through a light year of lead without a scratch. They are whispers of a deeper physics, but here is the extraordinary thing about them. In the presence of magnetic fields, they can perform a kind of quantum magic. An ALP and a photon, a particle of light, can oscillate into one another. They can transform back and forth. Picture a gamma-ray photon born in the heart of a distant blazar beginning its billion light-year journey to Earth. Along the way, it traverses the vast magnetized spaces between galaxies. According to this hypothesis, it might not make the entire trip as a photon. For a stretch of its journey, it could convert into an invisible ALP, slipping through the extragalactic background light like a ghost, immune to the absorption that would normally destroy it. Then, closer to home, in the magnetic field of our own Milky Way, it could convert back into a gamma-ray photon arriving at our telescopes. this process would have two dramatic effects on what we see. First, it would make distant gamma-ray sources appear brighter than they should be because their light has found a secret tunnel through the absorbing fog of starlight. Second, and more relevant to our background glow, this oscillation process would leave a subtle fingerprint on the gamma-ray fog itself. The constant conversion and reconversion of photons and ALPs across cosmic magnetic fields would distort the spectrum of the background in a unique, predictable way. It would add a specific kind of wiggle or modulation to the smooth curve of light. Astronomers are now scouring the data from the Fermi telescope and other instruments, not for a bump, but for this precise pattern of distortion. They are looking for the shadow of a particle that has never been seen, using the entire cosmos as its detection chamber. The implications of a discovery are staggering. Finding evidence for ALPs in the gamma-ray background would do more than identify a new source for the fog. It would crack open the standard model itself. It would prove the existence of a new fundamental force or field, a new piece of reality's underlying architecture. The faint, uniform glow that bathes us would become a Rosetta Stone, translating the language of the largest magnetic fields in the universe into a message about the smallest particles that could exist. It is a breathtaking long shot, but the potential reward is nothing less than a new chapter in physics, written in light we are only beginning to understand how to read. The search for whispers from the cosmic dawn pushes us to the very limits of what we can measure. The 20th mystery of the gamma-ray background asks if we can detect the faint, dying echo of the universe's first light. After the Big Bang, the cosmos was a dark, neutral sea of hydrogen gas. Then something changed. The first stars ignited, monstrous behemoths hundreds of times the mass of our Sun. They lived fast and died violently, and their blistering ultraviolet radiation began to tear apart the surrounding hydrogen atoms, reionizing the universe in a process that took hundreds of millions of years. This was the epoch of reionization, the moment when the cosmic lights truly turned on. These first stars and the small, chaotic galaxies that housed them were not gentle. They were engines of unimaginable violence, likely producing intense stellar winds, frequent supernova, and powerful particle acceleration. All of this turmoil would have generated gamma rays. But the universe was much smaller and denser then, and the light from that era has been stretched by cosmic expansion for over 13 billion years. Those once powerful gamma rays have been redshifted into the lowest, softest part of the energy spectrum, diluted to an almost imperceptible whisper. Theoretically, the combined output from every one of those first, furious structures should leave a faint, unique imprint on the very lowest energy band of the cosmic gamma-ray background. Finding it would be the ultimate archaeological dig, uncovering not bones or pottery, but the fossilized light of creation itself. It would give us a direct probe into the properties of those first stars and galaxies, objects we can never hope to see directly with optical telescopes. The challenge, however, is monumental. Separating this ancient whisper from the cacophony of the present is like trying to hear a single, distant flute note in the middle of a roaring rock concert. Our own Milky Way is a brilliant, swirling foreground of low-energy gamma rays, produced by cosmic rays interacting with local gas and starlight. This local emission is billions of times brighter than any conceivable signal from the dawn of time. Astronomers must create exquisitely detailed models of our galaxy's gamma-ray emission and subtract it from the total sky map with incredible precision, hoping to reveal the subtle, uniform residue from the early universe. Any error in modeling our own galactic backyard would completely swamp the signal. It is a task of staggering difficulty, requiring not just better telescopes, but a deeper understanding of the particle physics happening in every corner of our own galaxy. Yet the potential reward justifies the centuries of effort. If that whisper is ever found, it will not just be another source added to the cosmic fog. It will be a direct line back to the moment the universe woke up, a final message from the first giants written in the oldest light there is. Our own galaxy is a brilliant, swirling veil of light that stands directly between us and the cosmic story we are trying to read. To see the faint, extragalactic fog, we must first see through the dazzling glare of home. This is the 21st mystery, the Galactic Foreground Subtraction Challenge, and it is the most critical technical puzzle in the entire field. Every measurement of the cosmic gamma-ray background begins with an act of cosmic subtraction. The gamma-ray sky our telescopes capture is not a clean image. It is a messy collage. The dominant feature is the Milky Way itself, a blazing band of light across the center of the map, produced by cosmic rays slamming into interstellar gas clouds and starlight. This galactic foreground is millions of times brighter than the subtle, uniform glow from beyond. Isolating the extragalactic signal is like trying to hear a whisper in a hurricane. Astronomers must build an exquisitely detailed model of every process that creates gamma rays within our galaxy. They must account for the density of atomic and molecular hydrogen gas in every direction traced by radio telescopes. They must model the likely distribution and intensity of cosmic rays, those invisible particle storms as they swirl through the galaxy's magnetic fields. They must even account for the faint gamma-ray glow from interactions with starlight itself. Only then can they create a simulated map of what the Milky Way should look like in gamma rays and subtract it from the total sky map. What remains, in theory, is the pristine cosmic gamma-ray background, but here lies the profound vulnerability. Any error in that galactic model, no matter how small, does not simply vanish. It leaves a residual pattern, a ghost image of our own galaxy, imprinted onto the supposedly clean extragalactic map. If we misjudge the density of gas in a particular spiral arm, or underestimate the cosmic ray flux in the galactic halo, that mistake masquerades as a feature of the background itself. It could create a false anisotropy, a fake lumpiness, or distort the measured spectrum. This means that many of the tantalizing features we think we see in the background, potential hints of dark matter or exotic physics, could actually be artifacts of our imperfect understanding of our own cosmic neighborhood. The debates in the field are therefore intensely technical and crucial. Which tracer of interstellar gas is most reliable? How do we properly account for the gamma rays produced by electrons versus protons? Different research groups use different modeling techniques, and sometimes their resulting maps of the clean background show subtle but important differences. The entire edifice of cosmic gamma-ray background science is built upon this act of careful, uncertain subtraction. It forces a humbling realization. To understand the universe at its largest scales, we must first master the intricate details of our own galactic home. And even then, we must view every discovery about the distant fog with a cautious eye, knowing it might just be our own reflection. Subtracting our galaxy's brilliant foreground is a monumental task, but it is only the first step in a deeper cosmic accounting. Every new generation of telescopes brings us greater sensitivity, allowing us to peer deeper into the fog and pick out the individual points of light within it. This is the 22nd mystery, the puzzle of the missing point source fraction. For over a decade, the Fermi Large Area Telescope has been our most powerful eye on the gamma-ray sky, and its mission includes a relentless cosmic census. With each passing year of observation, it collects more photons, allowing its software to distinguish fainter and more distant sources from the uniform glow. It is literally chipping away at the cosmic gamma-ray background, resolving it into a growing catalogue of individual objects, blazars, pulsars, star-forming galaxies. The question is a simple one of percentages. How much of that once mysterious, all-encompassing fog have we now successfully explained by identifying its constituent parts? The latest analyses provide a fascinating and telling answer. Current estimates suggest that Fermi and other instruments have now resolved roughly 70 to 80% of the gamma-ray background into discrete point sources. This is a staggering achievement, a testament to our technological progress. The majority of the fog is not a true fog at all, but the blended light of countless individual cosmic catastrophes, just as the simplest theories predicted. Yet that remaining 20 to 30% is where the true intrigue now lies. This unresolved fraction is the hard core of the mystery. If our models were perfect and our telescopes infinitely sensitive, we would expect this number to keep shrinking towards zero. But a stubborn component persists. It refuses to be pinpointed. This could mean one of two profoundly different things. First, it could simply be that the remaining sources are so incredibly faint and numerous that even Fermi cannot pick them out individually. We might be looking at the collective glow of billions upon billions of ordinary dwarf galaxies or ancient pulsar wind nebulae, each one a candle too dim to see alone, but together creating a persistent, uniform shine. The second possibility is far more thrilling. That stubborn fraction might not be made of point sources at all. It could be genuinely diffuse, the signature of a process that fills the universe evenly. This is the realm of dark matter decay, or the accumulated cascade from ultra-high-energy cosmic rays, phenomena that are not tied to specific galaxies or black holes, but are woven into the fabric of space itself. The behavior of this missing fraction over the next decade will be our guide. As the next generation of even more sensitive telescopes comes online, will that 20% finally break apart into a swarm of faint dots completing the cosmic census? Or will it remain a smooth, enigmatic backdrop that no amount of sharpening can resolve, forcing us to finally accept that we are seeing the light of something entirely new? The missing point source fraction is the shrinking border of our ignorance, and what lies beyond it will define the future of cosmic discovery. The stubborn fraction of the gamma-ray background that refuses to be pinpointed is not entirely featureless. To find its hidden patterns, astronomers have devised a brilliant statistical technique that does not rely on seeing individual sources at all. This is the 23rd mystery, the anisotropy hunt. The word anisotropy simply means a lack of uniformity, a directionality. While the cosmic gamma-ray background appears smooth to our eyes, it must contain incredibly subtle fluctuations, tiny bright and dark patches, if it is truly built from the combined light of countless discrete sources clustered along the cosmic web. Finding these fluctuations directly is like trying to see the texture of a sheet of paper from a mile away. But what if you had a template? Imagine you have two maps of the same section of the sky. One map is the gamma-ray fog from Fermi. The other map is from an optical telescope like the Sloan Digital Sky Survey, showing the precise locations of millions of ordinary star-forming galaxies. You know these galaxies should be producing gamma rays from their internal cosmic ray storms. Even if each galaxy is too faint for Fermi to see alone, their collective signal should leave a mark. So you perform a cross-correlation. You overlay the two maps and ask a statistical question. In the directions where we see more galaxies in the optical map, do we also measure a very slight increase in gamma-ray intensity? You are not looking for a single match, but for a faint echo across the entire sky. The power of this method is extraordinary. It allows astronomers to detect the presence of an entire population of sources without ever resolving a single one. It is like proving a forest exists by listening for the rustle of a trillion leaves, even though you cannot see a single tree. These studies have yielded profound confirmations. They have statistically detected the gamma-ray glow of ordinary star-forming galaxies, proving they are a major contributor to the background. They have also traced the signal from active galaxies and quasars. This cross-correlation work is not just about confirmation, however. It is a powerful tool for elimination. Different types of sources trace the universe's structure in different ways. Normal galaxies follow the distribution of visible matter very closely, But certain models of dark matter, particularly those where it decays smoothly, predict a different pattern of anisotropy, one that might not correlate as strongly with the visible galaxy map. When astronomers perform these cross-correlations and find the gamma-ray fluctuations tightly linked to the maps of ordinary matter, it places severe constraints on those exotic dark matter models. It tells us that if dark matter is contributing to the background, it must do so in a way that mimics the clustering of galaxies, or its contribution is limited. The hunt for anisotropy transforms the smooth fog from a featureless mystery into a statistical treasure map. Every faint, barely detectable fluctuation is a clue, a whisper from a class of objects we are only beginning to count. By reading these whispers, we are slowly, painstakingly writing the inventory of the high-energy universe. The faint whispers we have been straining to hear are about to become a roar. Our cosmic detective story is on the verge of a new chapter, one written by an instrument of breathtaking ambition. The Cherenkov Telescope Array is not just another telescope, it is a fundamental shift in how we will see the high-energy universe. Currently under construction in the deserts of Chile and the Canary Islands, the CTO will be the world's largest and most sensitive ground-based observatory for very high-energy gamma rays. It will see with a clarity and depth we can only dream of today, and in doing so, it will turn the mysteries of the cosmic gamma ray background from questions into answers. Its power lies in its design. Instead of a single dish, it is an array of over 100 individual telescopes of 3 different sizes working in concert. When a gamma ray from space strikes the atmosphere, it creates a cascade of secondary particles. Each telescope in the array captures a slightly different view of that faint, blue Cherenkov light flash, allowing scientists to triangulate the gamma ray's origin and energy with astonishing precision. This is like upgrading from a blurry security camera to a network of ultra-high-definition eyes, all watching the same event from different angles. For the background glow, this means one thing above all else: the power of resolution. The CTO will see fainter and more distant sources than ever before. It will chip away at that stubborn, unresolved fraction of the background with a vengeance, resolving thousands of new blazars, radio galaxies, and pulsar wind nebulae. We will finally see if the missing point source fraction truly dissolves into a sea of ordinary objects, or if something irreducible remains, but its role goes far beyond just counting dots. The CTA's sharp spectral vision will dissect the high-energy excess with surgical precision. It will measure the exact shape of that bump at the highest energies, determining if it matches the predicted curve from dark matter annihilation models or if it aligns better with an astrophysical origin, like a hidden population of extreme blazars. It could provide the definitive fingerprint, ruling entire classes of theories in or out. Perhaps most thrillingly, the CTO represents our best chance to directly detect the Grison-Zatsepin-Kuzmin cascade, that faint rain of gamma rays from ultra-high-energy cosmic rays colliding with the cosmic microwave background. If that cascade is real, the CTA's immense sensitivity and its ability to see the diffuse, extended glow of such a process might be the key to pulling its signal from the noise. It could directly map the journey of the universe's most powerful particles. The CTO is more than a tool, it is a promise. It promises to transform the smooth, enigmatic fog into a landscape of stunning detail. It promises to either reveal the dark matter signature we have sought for decades or to finally close that door, forcing us down new and even more exotic paths. This next-generation instrument is not merely observing the mystery, it is preparing to solve it, turning the background glow from a cosmic question into a detailed map of reality's most violent and hidden corners. The final mystery of the gamma-ray fog reveals that we have been listening to the cosmos with only one sense. The cosmic gamma-ray background is not a solo performance, it is one instrument in a grand cosmic orchestra. To truly understand its source, we must listen to the entire symphony, a field known as multimessenger astronomy. For the first time in history, we are not just observers of light, we are detectives collecting multiple, independent forms of evidence from the same cataclysmic events. The gamma rays we have been discussing are just one messenger. The others are ghostly neutrinos and the ripples in spacetime itself, gravitational waves. Deep under the Antarctic ice, the Ice Cube Neutrino Observatory catches particles that are even more elusive than gamma rays. Neutrinos are cosmic ghosts, born in the same furious environments as gamma rays, inside supernova, around black hole jets, and in the hearts of colliding stars. They travel across the universe almost completely unimpeded, carrying a direct, unaltered message from their violent birthplace. Already, IceCube has detected a diffuse fog of cosmic neutrinos, a background glow that mirrors our gamma-ray puzzle. The crucial link is this: if a certain class of cosmic accelerator is producing both neutrinos and gamma rays in a predictable ratio, then by comparing the cosmic gamma ray background with the cosmic neutrino background, we can identify the culprit. A match in their patterns would be a smoking gun, pointing directly to sources like hidden blazars or star-forming galaxies as the dominant producers. A mismatch would be even more revealing, potentially ruling out entire categories of sources and pointing squarely towards something truly exotic like dark matter decay, which would produce gamma rays but very few neutrinos. Then there is the messenger of gravity. The Laser Interferometer Gravitational Wave Observatory, LIGO, has opened our ears to the collisions of black holes and neutron stars. These events create ripples in the fabric of space-time, and they too should produce flashes of gamma rays. Future space-based antennas will listen for a permanent hum, a stochastic gravitational wave background from all the merging supermassive black holes throughout cosmic history. This background hum will be a map of the universe's heaviest collisions. By overlaying that map with the gamma-ray background, we can ask a profound question: do the regions of space with the most violent mergers also glow brightest in gamma rays? If they do, it confirms that merging galaxies and their central black holes are a primary engine behind the fog. If they do not, it tells us the gamma rays are coming from a different, perhaps more subtle, process altogether. This is the ultimate power of multimessenger astronomy. It turns a single, confusing signal into a solvable equation with multiple variables. The gamma-ray background alone is a riddle. Combined with the neutrino background and the gravitational wave background, it becomes a cross-checked ledger of cosmic violence. Solving the 25 mysteries of this pervasive glow may not come from a gamma-ray telescope at all, but from a neutrino detector at the South Pole or a gravitational wave observatory in space. The final answer will be written not in one language but in three, a unified story of light, ghosts, and space-time itself, finally revealing the hidden engines of our universe. The invisible fog that bathes our universe is far more than just cosmic noise. It is a conversation, a complex dialogue written in the language of the most powerful light that exists. Our journey through its 25 mysteries has revealed a story that touches every corner of modern astrophysics, from the unresolved glow of distant blazars and the quiet hum of star-forming galaxies to the tantalizing possibility of dark matter decay and the echoes of evaporating black holes. Each piece of the puzzle points to a deeper truth. This background is not a single mystery to be solved, but a universal tool. It is a probe for particle physics, testing the limits of the standard model with whispers of actions and exotic particles. It is a census of galaxy evolution, measuring the total history of stellar birth and death across cosmic time. And it is a cornerstone of cosmology, offering an independent map of the universe's structure and the properties of the space between galaxies. Yet for all we have learned, crucial pieces are still missing. That stubborn, unresolved fraction of the glow, the precise shape of the high-energy excess, the final word on its perfect smoothness, these are the frontiers. They are the unanswered questions that drive the design of the next generation of telescopes like the Cherenkov Telescope Array and the next era of multimessenger astronomy. Deciphering this ancient, invisible light is how we read the hidden biography of the cosmos. Every photon in that faint fog carries a story of a cataclysm, a record of a force, or a signature of something entirely unseen. By learning to translate it, we are not just solving a puzzle, we are witnessing the universe's most violent and energetic history unfold before our new, unblinking eyes. Which of these 25 mysteries do you find most compelling? Share your thoughts in the comments below and subscribe to join us as we continue to explore the deepest wonders of the cosmos.